Hi, this is a class for October 29th, 2019. Remember, this is not a substitute for reading the textbook, and in some cases, if there are certain terms that you don't understand, that you look for them on the web or in other books. We're going to be talking about homonuclear diatomics and then later heteronuclear diatomics. Just as a brief review, for the first elements in the first row, we have the simplest species, which is H2+, only has one electron shared among the two protons. We have a bond order of a half, and this is the bond energy and bond length. If you add one more electron, we have a stronger bond and a shorter bond length. What causes the shorter bond length is the stronger bonding, okay? And then we have helium 2+ and then helium 2, okay? If you are curious, helium 2 does exist, and if you look on the web, the binding energy is very, very small, is 1 milli-electron volt. And then the bond length is approximately 60 angstrom. So as you can see, here they're all in the 1 to 2 range, even 0.7 to 1.1 range, and this one is really, really long, okay? However, don't let anybody tell you that helium-2 does not exist. It can be prepared and it can be studied. However, you cannot buy a bottle of helium-2 because it very easily falls apart. Okay. So now we're going to look at the second period atoms. And turns out that there are some simple things and there are some not so simple things to understand. And this is why it's good for me to explain. Okay. So we're going to see in a little bit that the 1s electrons barely participate in second row diatomics. And so we are left with the 2s and the 2p orbitals and the s and p interactions. So for example, if we have 2s orbitals, they form a bond just like the 1s orbitals. I don't think I need to explain that too much. However, there can be interactions between S and P because the pz orbital is pointing towards the other atom, as you can see here. So there's a little bit of bonding or interaction. That interaction can be constructive or destructive. And here we have the bonding between the pz and pz. Okay? They're both pointing into each other, and so they form a chemical bond. So those are some of the interactions. You might say, well, what happens with the other orbitals? So for example, if I have a 2s orbital, and then I have a px or py orbital, we find that, for example, here you would have some bonding interaction, but here you would have anti-bonding interaction. So there is a net zero interaction between S and the perpendicular p orbitals. Okay, perfect. Keep going. So in the case of the two PZs, we can have bonding. Okay, so here we have the constructive interference of the orbital, and we can have anti-bonding. Okay, notice that when we have anti-bonding, because there's electron-electron repulsion, there is additional density that moves out, so that these lobes are smaller and then these ones are larger. Okay, so here we have bonding and anti-bonding of the PZ. Now, as we have learned, this would be the sigma bonds. Okay, why? because if I make a cut here and I look from the side, it looks cylindrically symmetric. Called symmetry. And this is, so this would be the internuclear bond, and then you can cut, and this looks symmetric, similar here. Now, this one is antibonding, so we'll give it a star. In this case, we have the px and the px, and what happens is that we have constructive interference leading to bonding, constructive interference leading to bonding. So do not associate red with bonding and blue with antibonding. Blue and red signify the phase of the wave function, okay? So this would be the bonding, and as you can imagine, if we flipped one of this and it had the opposite phase, then we would have the antibonding. So let's look at that. So in this case, they are flipped, and we see now antibonding. Once again, because of electron-electron repulsion, we have energy density that moves away, and this is what causes the antibonding. This is now a pi bond, and this would be a pi star bond. Now notice that this is the p-axis, and we're going to see the same, exact same for the py's. So there's going to be bonding and antibonding for the py's. And then you might say, just for funsies, what happens if I have the following? Oops, sorry that my hand slipped there. So let's say that we have, we say just for fun, what happens if I have this orbital trying to bond with this orbital? Well, what we see is that there would be no overlap. And therefore, it's a non-bonding type of interaction. Okay? Not even bonding or anti-bonding, there's just nothing. Okay. So, one simple way of looking at this chapter is that we are going to fill the electrons according to the Aufbau principle and you know, the exclusion principle and maximum multiplicity principles. And so, for example, we know that we can put 2 electrons per orbital. So far, so good. And then we see here maximum multiplicity. Excellent. And then we have, you know, we keep filling carbon, nitrogen, oxygen, and fluorine. And this is all fine and good, and I'm sure many of you have done this before and can show that, for example, oxygen and boron are known to be paramagnetic because they have unpaired electrons. Okay? So this is very good, and then we see here that nitrogen has a bond order of 3, and we see that oxygen, it has 3 minus 1 from antibonding here. This is antibonding, and so this has a net bond order of 2. Okay, and similarly, carbon has a net bond order of 2. Okay, so what is the difficulty here? Well, what happens is that there's a trend here that is, I think, the hardest part to understand. The hardest part to understand is the following. So I'm gonna now make, actually I'm gonna change color. Okay, and now let's look at certain trends. We see the sigma 2gs that comes from the 2s orbitals is moving down in energy. Okay? We see that the sigma 2 star, sigma u star, is also moving down in energy. Okay, that makes sense. Interestingly, oh well, let's see what else is moving down. We see that this sigma 2pz is moving down in energy. Okay, yeah. Okay, the sigma upz moving down in energy. This one, but then we see that the pi not moving too much, and these pi's are moving down but not as much. Notice that here we have the 2 sigma 2pz, but that has moved down. Okay, turns out that this happens for all the elements beyond nitrogen. And I think that that's one of the most interesting things to study and to try to understand. Sure, one can memorize this, but I hope that most of you in Chem 181 would like to know why this is so. So we're going to dig down a little bit. So we have the 1s, 2s, and 2p orbitals that are going to be interacting. And how are those arranged in energy? So if you remember, we're now talking about atomic orbitals. So we put our Coulomb potential, and then we know that the 1s level is going to be here. The 2s is going to be considerably higher, and because there are now multiple electrons, the 2s and the 2p are not going to have the same energy. There's going to be a certain gap. Okay? A lot of what is going to be happening is going to depend on the gap between 2s and 2p orbitals. And that's going to be the key to why these energy levels in the atomics and the correlation diagrams changes. Now, when we talk about the energy levels, how do we know, what is the truth? What is the, how are these energy levels really arranged? Well, we use photoelectron spectroscopy. And if you want to learn more about photoelectron spectroscopy, there are a number of very, very good websites that explain to you how the instrument works and so on. The point is, as we were saying earlier, we have our Coulomb potential. In the case of an atom, this would be 0 energy. And then we would have, as we said earlier, the 2p and the 2s orbitals and the 1s orbital. And what we're going to be doing is shining X-rays until we release the electrons. So as you can see, the 1s orbital requires the most energy. That would be this one. And then the 2s and the 2p that are closer together are going to be as such. And so we really can see that the 2p is the highest, requires the lowest amount of energy. So notice that this is the binding energy. Whereas the 1s is really deep down. What we're going to see is that these 1s electrons are so deep down that they don't participate in bonding. In this case, these ones are the ones that participate, and these are what actually is known as the valence electrons, because they are the ones that participate in bonding. Okay? One of the things that we can do is we can flip the diagram to make it a little bit more compatible with our understanding. So what we would have is we would have the 1s orbital and then the 2s and 2p. Okay, so here we have a table that contains the energies of all the first of the second row elements, and here we can really see these trends more accurately because this table takes data from photoelectron spectroscopy. So we see that the 1s electrons go way down. How much down? For example, for neon, we're talking at minus 900. Notice here, minus 900. Okay? Compared to the 2s orbital, which is at minus 50. Okay? That's a humongous gap. Now, for having interactions, the interactions are strongest when the gap between the energy levels is smaller. Okay, so interaction is proportional to 1 over the energy gap. Okay, so when the energy gap is 0, strong interaction. When the energy gap is huge, very little interaction. So as you can see, the 1s orbitals would interact for hydrogen, for helium. By the time we get to lithium, okay, what happens for lithium? Let's see. For lithium, we have this point, that the 1s, I'm sorry I don't have very fine control now. This is minus 100, whereas the 2s is about, less than 10. So already for lithium, the 1s orbitals are not doing anything. Okay? Now let's look at the 2s orbitals. The 2s orbitals, similarly, are going down. Why are they going down? Well, remember, Coulombic attraction, and the nucleus is getting more and more positively charged, and so the inner shells get pulled stronger and stronger. So this one's going very fast down. And if we notice here, the 2p's are not going down as fast. Okay? Okay, so the 2p's are not going down as fast. What that does is that this forms an energy gap that is increasing. And perhaps this increasing energy gap is responsible for the change that occurs that we were talking about earlier between nitrogen and oxygen. Let's see if that's the case. Here, I am indicating how this energy gap increases, right? Now, one of the things that we know for certain is if this is the trend, then what we are for certain is that this gap between the 2p and the 2s will continue to increase. That means that for any atom that is larger than nitrogen, this gap is going to be sufficiently large that the sp interactions will be negligible. Okay? Sorry, my pen is not working, so I'm writing with my finger. Okay? But the SMP interactions are going to be negligible as you go to larger atoms, but for these atoms, particularly BCN, we have some sp interaction. Okay? Now, this sp interaction is not going to be not for px and and Py, but yes for Pz. Okay? Okay, so now let's take the energy diagrams directly from our atomic energies and try to make correlation diagrams. So this is the 2s and this is the 2p. Okay, and so we will have some interaction of the s. Very good. Then we're going to have the 2p's, and this are going to look like this. Okay, so what is happening? What is happening here is, of course, here we have the sigma and the sigma star from the 2s's. And then we're going to see that this level, which would be the sigma coming from Pz interactions, this one has been pushed up by this sigma antibonding, right? So the S to Pz interactions have pushed this sigma Pz binding orbital up, whereas these ones, which are the Px or the Py's, are not affected. Okay? Now, let's look at what happens with fluorine. In this case, for fluorine, immediately we see that the distance between the S and the P is so much larger that now okay, so not a very nice drawing, but what I'm trying to show is that in this case, this interaction is minimal. While in this case, the interaction of the 2s to the sigma, from the sigma star to the s from the pz's is not negligible, and so the double the pi is under the sigma pz. Okay? And so now we understand why for nitrogen we have a greater interaction between these two orbitals, which causes the sigma g 2pz to move up, whereas in the case of fluorine, we know that this energy is much greater, and so because the energy gap between S and P is large, so these drawings are not to scale, but because the energy gap is very large, there is almost no interaction here. Okay, and so there's no, so this orbital stays where it is. Okay, and again, in case you're wondering, why is the pi u 2px and pi u 2py, why that one doesn't move? So that one should be at the same exact energy as this one. That one doesn't move because it's perpendicular to the axis, and so any kind of interaction will cancel because of the change in phase of the p wave functions. However, so then the only one that gets affected is the sigma g2pz, and who is affecting it? It's being interacting with the sigma star u2s. The interaction large here and small for all elements that are z greater than 8 or equal than 8. Okay? Now, I hope that some of you say, okay, that makes some sense, but how do we really know? I want to go to the laboratory and measure and confirm that this is actually the way it is. And I applaud that. I think that that's really wonderful. So for that, we again go to photoelectron spectroscopy, and we look at the photoelectron spectrum from nitrogen. Okay, let's start from the very high energy. Okay, so what is at the bottom of the well? Well, we see the 1s electrons at 410 nanometers, 410 eV. So that's really, really far down, almost no interaction. Then we have the sigma G and the sigma star. Okay, so far so good. And then the question is, do we see the sigma U or do we see the pi U? Sorry, the sigma. Do we see the sigma or the pi? And what we find, it's a sigma G. What we find is that we have the pi U's before the sigma. So that confirms that for elements like nitrogen and with smaller atomic number, this is going to be the case. Okay, fine. Now let's look at the next element, for example, oxygen. Okay, for oxygen, we see that we have the 1s. Now don't be confused. This is 410, this is 545. I really like when plots are drawn from 0 to whatever number without any scaling and without any gaps. This scaling and gaps can make plots very, very confusing. Okay? But we have the 1s and the 1s. So far, so good. No interactions with the 1s's. Then we have the sigma G, 2s. Okay, slight difference, but actually they're quite close. Then we have the sigma U 2s star, sigma star, at about 25. Here we have the sigma U 2s at about 19. So there's a big difference. You see, I wish this would not have the gaps. Now, in the case of nitrogen, the next thing we have is the pi's, whereas for oxygen, we have the sigma G. Okay? Now, you will notice a few interesting things. First of all, what's the deal with all these peaks? Okay, those are vibrations. So this technique is pretty cool because it also allows you to see vibrations, and you can see the energy for the vibrations. That will tell you the strength of the bond and things like that. Similarly, here we see a lot of wiggles, which would be vibrations of oxygen. You will also see that the sigma of the pz is split, and this splitting is because it is interacting with what? It's interacting with this one, right? So this interaction is going to cause part of it to go lower in energy and part of it to go higher in energy. Okay? So interestingly, in the absence of this interaction, so the middle of this would be similar to the sigma from here. Okay? And then we have the pi's. Okay? And so so these are the pi u's, and then these are the pi u star. Okay? Let's remind ourselves, for the case of nitrogen, we would have so for the case of nitrogen, we have that type of correlation diagram, and for the case of oxygen. Okay, so let's follow them. Where is this binding sigma p? That one is here. Okay, and then we have the pi bonding, which is this one, and then we have the two electrons that would be here. Okay, now for nitrogen, we start with the pi, which would be this one, and then we will have the sigma G2PZ. Okay? Okay. What happens if we have a molecule like NO? Well, let's look carefully at this photoelectron spectrum. First, we see the 1s at around 545. And we notice that those electrons are not doing anything. Then we have the 1s from the nitrogen at 410. Again, I hope that this convinces you that the 1s orbitals for second row diatomics don't do anything. Then we have the sigma 2s, okay, sigma 2s, no problem, at about the same energy, okay. And then we have the sigma star 2s, sigma star 2s, sigma u 2s, okay, so far so good. And that was the easy part. Now the question is, are we going to see the pi orbitals first, or are we going to see the sigma orbital first? Well, as you can imagine, these are going to be really, really smashed together, okay? So what we see is that the sigma is split, okay? The sigma is split and the pi is here. So in a sense, it wouldn't be terrible to say that in the correlation diagram, the two are very, very close together. Just from this time on, we're going to take the configuration of the element on the left-hand side, which is the less electronegative, as the configuration that we're going to follow. So for NO, we may draw it like this. Okay, instead of drawing the correlation diagram like this, as if it was oxygen. However, is this one right or is this one right? Well, if you look, they're about the same. Okay, because of this splitting that comes from interactions with the sigma star 2s, it's, it would be very hard to say which one is the more correct. I mean, it would be more correct to draw them exactly at the same energy. Now, in a correlation diagram, if we make these two energies the same, then it would be a mess. So we pick the one of the element on the left, which would be the nitrogen, and so we will consider this to be a little bit easier to follow. Okay? Okay. So now let's look in terms of potentials and orbitals. So we have nitrogen and we have fluorine. First we have the sigma G2s bonding. Okay, fine. Notice that for nitrogen, the internuclear distance is smaller because we have a triple bond. Whereas for fluorine, we have an N=1 bond. Okay, so they're a little bit further apart. Then we have the sigma U2s star. Okay, this looks pretty much the same. Then, here's the interesting thing. For nitrogen, we first have the pi U and px's and py's, whereas for fluorine, we first have the sigma G2PZ. So basically, it seems that that what happened and what we have seen before is this one, this state repels this one and makes it move up in energy, and that does not happen in fluorine. Why? Because the S&P gap is much larger, and so in this case, this one has because there is no interaction, it's not pushed up, and so now it comes before the pi u px and pi u py. One of the things that is confusing in this diagram is it seems that this orbital moved up in energy. If the y-axis here, if this was energy, then this is not true, right? Because the pi u orbitals don't move; they're perpendicular to the bond axis, and so they're not affected by this SPZ type of interaction. So it would be much better had they drawn this at the same energy height and just show that this is what's happening. This one is the one that moves down in energy, or conversely, that this one has pushed this one up. Okay, so a lot of details, but I hope that this gives you more information about why the order between the pi u's and the sigma g's related to the p atomic orbitals move up. So now we go back to our diagram and we see that, whereas these orbitals are going down in energy, the pi's remain constant, and so somewhere around nitrogen and oxygen, this one's cross, okay? And then this trend will continue from now on in the periodic table, okay? And this is why we have n equals 7 and n equals 8, and that's why they're different. Okay, so I'm not gonna dwell too much on this table. You can study it. You will be required to know the electronic configuration, and then you will be required to show, for example, from a configuration, from any of this configuration, whether there are unpaired electrons. Unpaired electrons. That's, so this is my symbol for electrons. If there are unpaired electrons, then would be paramagnetic, determining bond order, bond length, bond energy, okay? And you're all welcome to explore what is the bond length and bond energy of helium-2. It's a little bit challenging. You may find that the article is something like measuring the weakest chemical bond or something like that. And then you will find that those values, okay? So based on the electronic structures, just like we saw with the atoms, that once you put the electrons, you get kind of periodic trends and so on. The same you can do, so we have the first row diatomics, and then we have the second row diatomics, and you can see how bond order increases and then decreases, and so bond energy increases and decreases, bond length decreases and then increases, and force constant increases and then decreases. It's all very similar. Pay attention to the cases when we have positive charges, okay? And similarly, you can have atoms with, diatomics with negative charges, so pay attention to that. And I think that everything else you can figure out from here. So now we're gonna be talking a little bit about heteronuclear diatomics. Now, it would be a mistake if we say, oh, hydrogen has a 1s electron and it will bind with the 1s electron from fluorine, with the 1s electrons from fluorine. But that is not going to happen. Why? Because the 1s electrons for fluorine are way down in energy, okay? Hundreds of electron volts down. So there's no interaction. So in order to make things fair, I took cuts from this table of photoelectron energies that we used earlier and place hydrogen and fluorine exactly, according to the energies that they should have. And so now what we see is like the 2s and the 2p electrons from fluorine can barely interact with the 1s from hydrogen. And then we need to see like what would be the closest for this to interact. And what we see is that the closest would be the 2pz. And so in that sense, we could draw a diagram like this. Okay? And that would be the 1s pz interaction. The other two p's just don't interact. So this would be the x and the y, no interaction. And what about the two s's? Again, no interaction. So that would be a good guess. Let's see how this really looks. Okay, so we find, to a little bit my surprise, that the book did this fairly well calibrated. So that's the energy of the 1s. This is the energy of the 2s. And this is the energy of the 2p's from fluorine. So the diagram that the book wrote is fairly accurate. And we see that the bonding is by the 2pz with the 1s. Okay. Now the bonding, the strength of the bonding gets smaller and smaller as the gap between the orbitals increases. Okay. And so what do we see? We're going to arrange heteronuclear diatomics such as A, B, putting the more electronegative on the left-hand side, okay? And then we're going to find the interactions according to the atomic energies, okay? Now, we have been following the linear combination of atomic orbitals theory, which is a great method for us to try to understand chemical bonding. And then if we want, so this is the qualitative method. So this is drawing these correlation diagrams. Correlation diagrams are qualitative, okay? They're qualitative. If we want to be more quantitative, then what we do is we use a computer that has the ability to calculate, hundreds and thousands of these diagrams, and then combine hundreds and thousands of atomic orbitals in order to improve the energetics. So how do the orbitals look? In the case of the 2s, they're non-bonding. So notice sigma non-bonding. Then we have interaction between the 1s and the 2pz. This is where the bond for HF is responsible. We have the pi orbitals, just no interaction because there's nothing here, so no interaction. So again, non-bonding. And then we have the antibond between so this would be the sigma star between the 1s and the 2pz, okay? That's kind of a cool orbital. And the book doesn't explain, but I picked it up. Suppose that we have the 1s trying to interact with the px's and py's. We see that whatever is gained from this interaction will be lost from this interaction. So again, no interaction, non-bonding. Okay? So again, to summarize, atom A is less electronegative, atom B is more electronegative, let's say higher Z. So the Z of atom A is less than the Z of atom B. And so that means that the p orbitals have moved down, okay? And so these interactions are less strong. So if you notice, the amount of energy that went down here and here is smaller. It's much larger when they're equal in energy, okay? So homonuclear diatomics have stronger bonds. And then we see that we fill the electrons according to, maximum multiplicity and Aufbau principle, okay? Here. And so you can try to figure out which heteronuclear diatomic this might be, okay? I leave it for you to figure it out. You can count the electrons. We have 2, 4, 6 electrons up here, and here we have 2 and 1, and that should tell you what might be this molecule, okay? So to summarize what we have been studying, we're using this linear combination of atomic orbitals to qualitatively understand chemical bonding from a quantum mechanical point of view, but without having to have major computers and so on. And even though this method is qualitative, we are able to predict bond order, bond energy. We are able to predict if it's paramagnetic. So we can predict all sorts of properties and trends, like in the periodic table, all without requiring a single, not even a calculator. So that's the beauty and that's the strength of this LCAO method. The problem is that it's really not accurate. If we want quantitative results, then we need to understand that the atomic orbitals, the AOs, were designed to fit around an atom. When we have a molecule, now the wave functions, to be optimized, we need a wave function that encompasses all of this volume in order to be accurate. And so the quantitative linear combination of atomic orbitals, what they're going to require is that we take higher and higher and higher and higher orbitals, so high that they encompass the entire volume. So we do that for one of the atoms, we do that for the other atom, just, hundreds, sometimes thousands of atomic orbitals, and then by linear combinations of them, we're able to reach a very high accuracy and match the experimental results of bond energies and so on. So that's the summary of this chapter, and this is what we're covering this week. I hope to see you on Thursday when we're going to have a quiz, and I will also send you a homework. Okay, see you soon. Bye-bye.